Yeah, thanks, Lars. Thanks for the chance to chat here. I was given only two pieces of guidance, I guess, from the organizers. One was, don't use the term multi-messenger. Everyone's sick of that catchphrase.
And it's outlawed. I've outlawed it.
You outlaw. Oh, that came from up high. Okay, so yeah, no. So I said light and gravitational waves in my title. And then the second was try to review kind of all the activities, the broad activities going on in this program, which is much harder because it's a very broad program. It's covering not just neutron star mergers, but also stellar mass black hole mergers up to supermassive black hole mergers and all the attendant physics of, stellar evolution and galaxy evolution and nuclear physics and nuclear synthesis and all this stuff. So it's really impossible to cover it all. It makes for a very exciting and interactive program, but it makes it difficult to try to cover it all. So I'll try to give a little bit of a broad, shallow feel of kind of the landscape of what things they're talking about, and then go a little bit more deeper into the neutron star mergers, and hopefully you get a sense of what's going on and can follow up if you're interested in some of the talks going on or with some of the people here on those subjects. So, although these are complicated systems, particularly neutron star mergers, you have a whole range of physics. You have general relativity, you have hydrodynamics, you have nuclear equation of state and nucleosynthesis, atomic physics and radiation transport. Very messy, complicated problems, but when you try to do a Blackboard talk like this, you see that a lot of the basic theoretical picture can be laid out in these little sort of twiddle arguments. And so some simplicity arises out of the complexity. I'll try to express a little bit of that today, but we'll see how much time I have. But the general picture we're thinking about is a simple one. Just, a binary star system or binary black hole system. Stars of radius A at some separation A away, some mass m. And I won't go into much detail about, the different mass ratios or spins or other details that can be in the system and the eccentricity. But I can just talk about, these can range from very large scales, from stellar mass up to millions or billions of solar masses. If we want to get some feel for the landscape of emission, we'll see. So I'll try to lay out sort of the landscape of gravitational waves and then go a little bit more into the light. And so gravitational waves, we like to characterize, the basic properties of gravitational waves from this system, so their frequency and their amplitude. And we can do some simple arguments for that. The frequency is relatively straightforward, just in Newtonian dynamics. If we want to take the period of the system, just the circumference over velocity, or velocity, you could just use the Keplerian velocity. It gives you a frequency essentially of dropping numerical factors, as I'll do throughout. GM over a third square root of that. And so the idea is as these systems come closer and closer together, the frequencies get higher and higher, and that's that characteristic chirp signature you see in the gravitational wave sources, is the frequency rises higher and higher. The actual merger, if we're going to get a sense for the frequencies involved, we can think at merger, because when the separation becomes of order the radius of the stars, and some interesting dynamics happens there. If we're thinking about black holes, the relevant radius is the gravitational radius, Schwarzschild radius. This is frequency 1 over period. The gravitational radius, just the Schwarzschild radius for a non-rotating black hole, 2gm over c squared. And if we plug that in, we'll get a merger frequency. That's essentially basically c to the third over gm. Okay, so for black holes, and you can plug in numbers there, and you'll get something like 10 to the 4 so the sun. Right, so scale to the mass of the sun, the frequencies of the gravitational waves at the time of the merger are going to come out in this range. So you get a feel for the range of frequencies you can have. The mergers of 10 or so solar mass black holes that LIGO has seen and continues to see are going to be sort of in the hundreds of hertz range. Supermassive black holes at 1 million solar masses maybe down at like 10 to the minus 2 hertz, or 100 million solar masses might be up at 10 to the minus 4. And the neutron star mergers, which have masses about a solar mass, but they actually have radii, they're maybe an order of magnitude bigger than their Schwarzschild radii, will have frequencies sort of around kilohertz range, right? And so that's the frequencies that we expect to see. Now one can ask, if that's the frequency parameter space, what about the amplitude of the wave parameter space? And we can make a simple dimensional analysis of that as well. You can think about the potential of the field and the far limit. So potential of some gravitational field, well, if you have a point mass at some distance d, potential will be something like gm over d. Of course, we want the potential due to some radiation field that's propagating away to infinity. And by analogy to electromagnetic waves, dimensionally, the dipole term, its potential is going to be reduced by some ratio of your dipole size, the size of the system A, over the wavelength of the light that is being emitted, which is just, since these waves travel at the speed of light, it's just the wavelength just c over the frequency. Now, it's well known that gravitational waves have no dipole emission because a conservation of linear momentum. You move a mass this way, there'll be an equal movement in the opposite direction to balance momentum. So the dipole term disappears. So you get the next highest term, the quadrupole term, where you square this dimensionless parameter. The sort of the multipole expansion is an expansion in this dimensionless parameter. So the leading term is basically this, which I can replace lambda with a frequency if I want. And then what you hear the gravitational wave people talk about all the time is the strain, which really defined as a dimensionless form of this potential. And this potential has units of velocity squared. So it's defined as that potential over a characteristic velocity, speed of light squared. And then we can put this together and we get just a dimensional analysis expression for the amplitude here. There should be a square here. Sorry about that. A squared here. Sorry, a little too quick. So that's an estimate of the strain, and the reason the strain is interesting is it turns out to be an estimate if you have some detector with some length L of test masses. The relative displacement of those test masses, the delta L that they might move over their length L, is basically given by the strain, which I could show if I had a little bit more time. It's these sort of hand-wavy arguments, but basically the potential, gradients of the potential are telling you about the acceleration of objects. So, H this way, telling you about the small displacement that experiments like LIGO mentioned. And sorry if I missed another factor here. A little more careful. See the force. So you get the basic feel of what the strain will be. There's a prefactor here, G, which is a relatively small number over c to the fourth, which is a big number. So the strain is a very small quantity. You have a quantity here that's dimensionally the quadrupole moment of the system. In a real analysis, you would actually get sort of the second time derivative of the quadrupole moment, which would bring up this frequency squared. So that's the basic field for what we expect to see from the strain. Again, we can plug in, if we're interested in a characteristic strain at the time of merger, we could plug in the frequency at merger there and the value of A at merger. And you'll get something that looks like dropping on the factors, GMC squared over D, which is just, turns out to be order of magnitude, the Schwarzschild radius of the star over the distance. Okay. So now you can estimate these strains in your head if you want. Stellar mass black hole has a radius of about 1 kilometer at a distance of some, 100 megaparsecs or so, something like 10 to the 21 kilometers. So this will be of order 10 to the minus 21, this very small displacement that LIGO famously measured. Interestingly, is related to just the ratio of the size of the black hole to the distance away it was. Okay? And so you get a sense of where these things lie in parameter space and how they can scale with mass. And one can go on with those sort of arguments and estimate how much energy is lost from the system and how fast the system will in-spiral. But we'll kind of leave it there and just map out a little bit of the parameter space that people are looking at here. Log in the frequency and log in the strain. Now what you usually see when people plot strains in this kind of plot is not the actual strain, but a characteristic strain. Which is essentially the strain times the square root of the number of cycles. This sort of stays in the band that you observe it for. This is at least one way to plot it, and that's just because if you have a source, you can observe it over many cycles. The signal to noise you'll measure will build up by square root of the number of cycles, and you could estimate as well what that would be. But essentially, the landscape looks like this. You have at the higher frequency range, say 10 to the 2 hertz, you have LIGO sensitivity here with the black hole binaries. This range, binary neutron stars, coming out to about the kilohertz, so actually peaking out a little bit outside the LIGO band, and actually the merger of these neutron stars are actually a little bit outside LIGO sensitivity. So what we really see in the binary neutron stars is the in-spiral phase leading up to that merger. You can go a little lower if you want, like 10 to minus 2. So this is LIGO. Lisa will sit somewhere here, and this will be where the supermassive or massive black hole binaries will sit. 10 to the 6 solar masses or something in that range. And then even further, if you go very low in frequency, not quite to scale, I guess, but the pulsar timing arrays are kind of in the nanohertz range. So actually won't see mergers, but we'll see binary systems in the earlier phases where their separation is larger and the frequency is lower. Right? And so you get kind of a feel for what things are talking about. And in each of these topics, there's a rich array of things to discuss. So there's a lot of discussion about the binary black holes, stellar evolution. How do you get these systems of, massive black holes emerging? Do they come from binary massive stars that form black holes? Do they have been dynamically captured together in some dense system like globular clusters? And other possibilities. What is the maximum mass we think a binary stellar mass black hole could have? Some indication of stellar evolution, there might be a gap above 50 or so to 120 or so solar masses where you don't get black holes. So if LIGO sees something in that range and it's finding these things now, what does that mean in terms of how these systems form? And a lot of other sections, and I think Emmanuel Berti and others will have talks on this. You can learn more about all that interesting physics. Again, a lot of stuff going on in massive black hole binaries, how they form and evolve in galactic systems. What would be electromagnetic counterparts to these systems? Black holes themselves, like they're not producing any interesting light, but the binaries could have a gaseous disk surrounding the binary that could feed gas into accretion. And there were talks that unfortunately I missed because I wasn't here yet, but modeling and simulating accretion in a binary system and looking at sort of the periodic light signals that you might see and how you might use those to find a counterpart to this system. And it seems like that is a more complicated and less distinctive signature that you might have compared to the binary neutron star, but still a lot of work trying to iron out that as well. And you can also ask what might be in the gaps here. I mean, if you care about white dwarf stars merging, you could estimate their frequency. They have masses around a solar mass, but radii about 1,000 times that of neutron stars. So they're kind of lying in this range here, in kind of the gap between LIGO and LISA, and their strain also will be somewhat lower. So would there be capabilities to explore that range? I would love to see that, because you could finally answer the question of where type 1a supernova come from if you saw two white dwarfs merging and then you saw a supernova come out of it. And core collapse supernova, other supernova might also be in the kilohertz range, but likely give a weak gravitational wave signature, because if they spherically collapse, there's no quadrupole moment. So to have some reasonably strong signal from a supernova, you need some asymmetry in the supernova. Maybe if it's rotating rapidly, you can have a quadrupole moment. But that will be rare, and we would have to get a very close by supernova to actually do it. So, well, there's a lot more to say on all these things. I'll leave it at that and let you follow up with other people and other talks this week. And focus a little bit more on the binary neutron star. We had one great event like this in 2017. There's been two more events LIGO has announced, or candidate events at least in the last ongoing run. Those two were further away. They haven't found any electromagnetic counterpart to them that's unclear. So the first one in 2017 was definitely a very special kind of event, but you can hope for more of those coming forward. And there's a lot you can learn from these binary neutron stars. In particular, I'll talk a bit about constraints on the equation of state of dense nuclear matter in a neutron star, which is an interesting theoretical topic, as well as nucleosynthesis that you get out of binary neutron stars. So formation of heavy elements in the debris that gets kicked out in the neutron star. And I'll try to at least give the picture of those and point to where some of the interesting details lie. Okay? So let's talk a little bit more about that. I'll start talking a little bit about the equation of state, and then I'll say a little bit about the mass ejection that forms heavy elements and the associated emission that we see from those, called the kilonova. Equation of state is an interesting topic. We'd like to know, how soft or stiff this exotic nuclear matter is in a neutron star. And LIGO gives us an interesting way to probe it, because you're actually kind of squeezing and tearing apart neutron stars. Of course, a lot of the interesting action happens outside of the band where you wish you could see it, so there's some motivation to try to push to higher frequencies to actually see the stars merge together. But even in the in-spiral phase, you can get some constraint on the equation of state, basically because the tidal forces of one star will induce a quadrupole moment in the other star, and that will contribute to the gravitational wave emission and lead to some enhanced in-spiral of the system. And that's usually characterized by some factor of the deformability, which basically characterizes, how much the system responds to a tidal force through some dimensionless parameter people use, something like some numerical constant, a love number, times the radius of the neutron star over its expected gravitational radius if it was a mass to the fifth power. And so essentially, if you can constrain from the gravitational waveform this deformability by looking at its impact on the gravitational wave signature, this kind of post-Newtonian approximation is sort of a leading order term associated with this effect. If you can measure or constrain that, you can measure and constrain the radius of the neutron star, and that'll tell you something about the equation of state of nuclear matter. How stiffer equations of state will have a larger radius, softer ones will have more compact. And so that was done for the gravitational waves seen in 2017 by analysis of the gravitational wave spectrum, and we have experts in the room that will tell you the details of that, and Jocelyn and Duncan and others that have worked on this topic. But essentially, there was not any clear indication that there was a term contributing from deformability to the gravitational wave signature. So that effectively sets some upper limit on how much this deformability can be, something like some number here, which, you can correct me if I'm wrong, but something of order 600 in this units. depending on how you do the analysis, which limits the radius of the star. It could be not too big, or else you would have seen this effect. You can ask, can we constrain this below? And gravitational waves don't give you a very strong constraint, a lower limit on this lambda. But it turns out the electromagnetic emission can be tried to use to put a lower limit on that. And works by people here, and David Radici and others would say that the electromagnetic emission is giving you something that the lambda is greater than about 300 or so. And I'll talk a little bit about what's setting that limit and what sort of uncertainties may be associated with it. But the joint light and gravitational waves basically kind of pin down some constraint on this deformability, which can be converted to a radius of the neutron star, something in the range. I think this is at least one number I've seen, 12 plus or minus 1 kilometer, so bounded roughly by a kilometer on either ends from these constraints. Which seems like a pretty nice constraint. It rules out some equations of state that people have proposed, but it still allows for a pretty wide range of different equations of state.
I'm sorry, it's an upper bound, or this, the minus 1 is something I should take seriously as a lower bound as well?
Yeah, the upper and lower bound, because of the upper and lower bounds basically on this deformability parameter. So a lot goes into this that I'm glossing over. There's inputs you can do from nuclear physics and sort of basic physical considerations that help with these bounds. Basically, depending on exactly on what you put into your priors in your analysis, this number may vary by some factor, but at least this is.
Qualitatively, what does it say about the equation of state?
Well, it's sort of in the middle. It's not super soft. It's not super stiff. So some of the super soft equations, you have too many degrees of freedom from, say, some kind of quark matter or something that can often restrain matter. You get some soft equation of state in a smaller radius, and those seem less preferred.
How much variability do we expect from neutron star to neutron star? Like, this is staying about one event, I assume. But is there variability in different neutron stars, or that they all always very close to the same, basically?
Well, what might vary is the mass, so that will change this parameter in the radius at some.
Yeah, but
the mass radius dependence will depend upon equation of state. But for a given mass, the thought is that, it's the same sort of stuff. The equation of state should be the same. So for a typical neutron star mass, this radius should be fairly universal.
I see.
It still varies, though. I mean, it depends on what kind of equation of state. Because there are equations of state where you can actually have at higher masses significantly smaller radii. So, it really depends on the theoretical model that.
Yeah, you would get a better.
We need certainly more events.
You would get a much better constraint on the equation of state if you had radii for different masses, because that would probe sort of the equation of state in different density regimes.
How well determined is the mass?
What's that?
How well determined is the mass?
Well, the mass, there's some kind of combined mass, the chirp mass of the system is constrained very well by the gravitational wave signature. And decomposing that into the individual masses is a little trickier because it's somewhat degenerate with what you say the spins are. So I think that's all folded into these analyses. And again, they go well beyond what the very surface picture I'm painting here, but there are experts around who can tell you all about the details. So that's one interesting result we see is some constraint on properties of neutron stars and the equation of state. And the other, which will be related, is talking about the mass ejected in a neutron star and the kind of electromagnetic signatures we get from that, and how those affect the questions of equation of state as well as origin of the heavy elements. So in a neutron star merger, some amount of mass, not a large amount, but some we think is ejected from the system. I can't draw you a simulation here, but I can give you sort of a generic picture of what the system looks like after the merger is over. And essentially you get some central remnant, most of the mass going into the central remnant, surrounded by some centrifugally supported disk of material that got hung up around the central remnant. And so that central remnant may initially be a neutron star, a pretty massive neutron star, because you've thrown two neutron stars together and most of the mass is here. That may collapse either promptly or after some delay to a black hole. And that's also one of the big questions people are asking, sort of, how massive could the neutron star be and remain stable? If it collapses, what's the delay to either reduce the differential rotation or other effects that may temporarily support the neutron star? Right? And there's arguments related to the electromagnetic emission that Ben Marguerite and others have done that suggest that in this particular case of the 2017 event, this neutron star collapsed to a black hole after not too long a time period. And maybe I'll mention a bit about that. But in general, this is the scenario you get. Some matter got flung out in the merger itself, either tidally stripped off or squeezed out when the stars came together. So you'll have some stuff out here, some dynamically ejected material. And, the GR simulation suggests this may be in the range of 10 to the minus 4 to maybe up to 10 to the minus 2 solar masses, probably not much more, so only maybe up to 1% of the mass or so gets flung out at some speed of about 0.3 c, which is basically escape velocity from a neutron star. This mass, we think, is too small to explain the kilonova emission that I'll talk about in a second. So we think there was more mass ejected. And the picture is that maybe most of the mass that was ejected from the system came out of this disk. The mass of this disk can be larger, maybe 0.1 solar masses. And over time, it's going to take a longer period of time, so maybe hundreds or thousands of orbital times, viscous effects will cause this disk material to accrete onto the black hole. That's where you may get a relativistic jet, produce the gamma ray burst and X-ray and other non-thermal emission we saw. Another rich topic that I won't go into. But in the process of this accretion, the viscous heating in this disk likely imbibes a lot of the material as well. And so you'll have material flying off of this disk in winds. And they'll move at about similar speed, a little slower, maybe about 1/10 of the speed of light. The scale of this system here is maybe about 100 kilometers, this disk. And so the escape speed's a little lower than from the neutron star itself. And so to try to understand this process of how matter gets ejected as this material accretes, you need to run simulations of this disk accretion that include GR and magnetohydrodynamics and resolve sort of rotational instability that occurs in the disk. Because it's really amplification of magnetic fields in this disk that give rise to the turbulence that kind of drives the viscous effects and transport of angular momentum that causes material both to accrete inwards but also get heated and blown out of the system. And so it's been studied for some time, but it's really only in the last year or two that we've had sort of detailed GR-MHD simulations that follow this evolution over hundreds and thousands of orbital time and actually saw jets being formed and winds getting blown off. And generically they find that the mass that gets ejected is roughly about 40% of the mass of the disk. So maybe 60% goes into the black hole and 40% gets unbound and flies away. And so, given that the disk mass can be something like 0.1, you can get maybe up to 4 or 5% of a solar mass ejected from the disk, which is likely larger than you get ejected from the dynamical crashing of the stars together in the first place. Yeah.
Can you give me a notion about timescales? Like, does this all happen instantaneously? The formation of the disk, the ejection, the neutron star to black hole.
So they're
collapse. So are these things all happening basically at the same time, right away, or is this sort of this delay of days, weeks, years?
Okay, that's a good point. So the merger itself, this is happening at kilohertz frequency. So sort of millisecond time scale, it's orbiting and this material gets spit out in sort of millisecond time scales. And then this disk continues to orbit on sort of millisecond time scales. But the time scale for this actually to accrete and to eject is a longer time scale. It's a viscous time scale for there to be angular momentum transport so matter can go in and out. And that's usually about, maybe 1,000 times longer. So over a period of a second or so, this disk is accreting in and being blown out. And that's all the action that's sort of the time scale for all kind of the dynamical action. And then what we'll see afterwards in this kilonova will be basically the aftermath of that, the debris from that sort of event. So
And how long did jet exist? Also on the second scale?
Yeah, along the same time scale, the accretion is powering this jet, so it may be forming over a period of a second or so. It may take some time to burrow through this cloud of dynamical ejecta there. And in fact, that time scale for it to sort of make it out of the system may be related to the fact there was a delay of about 2 seconds between the gravitational waves and the first emergence of the gravitational wave signatures. At least that's a sensible explanation for why there was that sort of delay. But we can see, and most people agree now, that most of the mass that got ejected from the system, I think most people would say, was coming from this disk here. And this is really where this constraint on the tidal deformability from electromagnetic signatures come from. Because by analysis of the light, we'll see from the kilonova, which I'll talk about in a second, there's indication we saw about 5% of the solar mass of material ejected. So more than we can get dynamically, but maybe we can get from the disk if the disk is massive enough. But if the stars are too compact, if their radius is too small, the tidal deformability is too small, you don't get a big enough disk. So the disk mass kind of scales with this tidal deformability. And to get enough mass in the disk of about 0.1 solar masses, you need tidal deformability of about that range. And so that's where the constraint comes from. You can think of it larger radii, stars as they come in. There's sort of more material at large radii with angular momentum enough to form a disk outside the innermost stable orbit. And so, one can ask about the systematic errors on this kind of constraint, and you can see there's probably many. One in about, simulating how much mass is formed in this disk, simulating how much mass gets ejected, and then trying to simulate from the observations how much mass we think was actually there in the system. And so those are all hard to quantify, but make me feel like this lower bound is maybe less secure than kind of the upper bound from gravitational waves directly, but gives us a sense of something that worth continuing to study. Okay. So we get this mass flying out. What's interesting about this mass is that eventually this cloud of debris that will form into heavy elements and will give rise to some observable optical infrared signature that we call a kilonova. And to think more about it, we can say, well, what's the stuff that actually gets ejected? What's its composition? What's it made out of? And probably in this disk, it's made, it's basically just free nucleons, protons, and neutrons, and electrons. But as it expands and cools, it will assemble into heavier elements. And so we can ask a little bit about the composition of those outflows and whether they make the heaviest elements in the universe. And that's usually parameterized at a rough level by trying to characterize the neutron richness of the system by this electron fraction parameter, which is basically equivalent to the proton fraction. So it's the number density of protons over the number density of protons and neutrons. And so for a system that's neutron rich, that has more neutrons than protons, that'll be less than a half. And we think, since a neutron star originally starts out very neutron rich, maybe YE of 0.1 or less, the material ejected here may have a significant excess of neutrons. And that really sets up the conditions for forming heavy elements in this outflowing material by this process of rapid neutron capture, which is a whole topic in itself that, again, I won't go into. But the basic idea is you can start with seed nuclei of normal size like iron or so, and just bombard them with free neutrons and capture neutrons on them at a rapid pace. And basically, those neutrons will beta decay to protons, and you'll work your way up to the periodic table to the heaviest elements. What's that?
Where do you get iron from?
Well, basically, these, the protons and neutrons here will, reassemble into first, alpha particles, and those alpha particles will fuse up the alpha chain to iron or some other seed nucleus, depending upon the actual conditions in there. So you have sort of, different fusion reactions that sort of build you up to some seed, and then to go farther than that, you require this sort of bombardment with neutrons. And so to build up to the heaviest elements, you want to have, the more neutrons you have, the better, because you can bombard these seeds more dramatically, and you can build up to heavier and heavier nuclei. And It's one reason why people think neutron star mergers are one of the prime sites in the universe for making these heavy elements, because there's not many other cases where you liberate a very neutron-rich gas from some system.
Density should be high enough.
Maybe in a supernova where you form a neutron star, you might get conditions like this. But it seems that those are not nearly as neutron-rich as the neutron star merger as well. So how neutron-rich are the outflows? Well, the neutron star, again, initially it's a neutron star. It's very neutron-rich. But the outflows themselves will be less neutron-rich because there'll be weak interactions. There'll be neutrino irradiation. There'll be neutrinos flying around here that irradiate the winds and other things. And those neutrino, interactions, these charge current weak interactions, can change protons and neutrons to each other and modify this YE. And since you're radiating, with both neutrinos and antineutrinos, the general effect of the neutrino radiation is to bring YE from a low value up to something closer to a symmetric value of a half. And so when you look at these simulations, what you generally see, if you look at the material flying out, what its composition is, you make some kind of histogram. Here's 1/2 a symmetric matter. Usually there's some broad distribution of stuff that's gotten more or less irradiated. So you see some broad, distribution like this. Or YE. Some of the stuff is quite neutron-rich, very low YE, and some of it is more symmetric. And there may be some geometrical dependence here. Neutrinos really radiate this polar region. So the polar region is probably on the higher YE range. The external equatorial regions are probably less.
The neutrinos are thermal or?
Yeah, thermal neutrinos, because cooling from either the inner parts of the disk, or if there's a neutron star here that survives from some period of time, it will be a strong neutrino kind of light bulb. So since the disk is hot, basically neutrino cooling is the dominant effect. And so this breakdown here, I kind of put this value of 1/4 because despite all the details of the complexity of these building up heavy elements by this repeated neutron capture, where you have to run complicated nuclear reaction networks to model it, roughly speaking, if you're very neutron-rich, below 1/4, you tend to make heavy elements, greater than atomic masses of 130 or so all the way up to the gold and the platinum and the uranium and stuff like that. Maybe even transuranium if you're very low YE. And if you're above 1/4, you tend to make lighter elements. So strontium or other lighter R process. And transition here is not completely sharp. It depends upon other things like the entropy and so on. But it's actually a relatively sharp distinction here due to some basic considerations from nuclear physics, essentially. Right around this mass number, there's a nuclei with the closed shells, like n equals 82, magic number for the neutrons. And that gives you sort of very stable species that act as sort of bottlenecks in the flow. So you hit those, if you have enough neutrons, you can get over that bottleneck of these very stable nuclei and move to the heavy range. If you don't, you get stuck here. And there's sort of a sharp transition. But if the simulations are right, that this material flying off has some wide distribution of YE, we'd expect we produce both heavier and lighter elements in the neutron star merger. Maybe we can explain the entire heavy elements that we see in the sun or something from one event. But the details of this distribution, I think, are still an active area of studying because, the neutrino transport is one of the things that's done most approximately in the simulations. It's one of the hardest problems. There can be interesting neutrino physics that comes in and modifies things in collective neutrino oscillations and other things. So this is one of the areas I think we'll see a lot of work and improvement is trying to predict a little bit better how neutron-rich these outflows are and what that means for the elements that we produce in the neutron star merger. In any case, at the end of the day, we have some outflow of mass that's probably formed of these wide distribution of heavy elements, and that basically debris from the system is what gives rise to an electromagnetic counterpart that we call the kilonova. And basically all the kilonova you can think of is just some roughly spherical cloud of debris that's expanding away from the from the system with masses of order 10 to minus 2 solar masses, or maybe 5 times that, and velocities of order 0.1 c. There may be some asymmetry here. You may get lighter elements in the polar regions and heavier in the equatorial, but there's somewhat details for what we're saying. And it'll have some radius. Now, after just a minute of being ejected, this material has moved far away from the site of the ejection. All the hydrodynamics and nuclear reactions and stuff freeze out, and you just have this serenely expanding cloud that's basically
Never
moving.
heard somebody call it serene.
Yeah. Well, okay, this cloud of nuclear waste, essentially. You might get from a nuclear bomb, or if you took nuclear waste from a reactor and threw it into space at the speed of light. That's what you would get. So maybe it's not so serene, but it's no more hydrodynamics going on. And the radius is expanding basically like velocity times time. So for a velocity of 0.1 c, this is of order, say, 10 to the 10 t over days, kilometers. So in one day, it's reached about 10 to the 10 kilometers. It's about the size of the solar system. So expanded from a very large range from here. So now you have a very low density cloud. And essentially, this is when, we can see in a second, that cloud will start to become translucent, and we can start to see light coming out of it, primarily optical and infrared light, maybe some UV. Questions on it? So, essentially, there'll be energy inside this cloud. It'll be hot. I'll talk a little bit in a second about where that energy comes from. And so photons will be kind of diffusing and random walking through this opaque cloud to try to escape. And basically the time scale of the escape can be estimated simply as well. You know, the diffusion time for the photons trying to come out of this opaque cloud, it's just a standard diffusion time, so we can write it as the optical depth of the cloud over the radius of the kilonova times the speed of light. The optical depth is just the radius over the mean free path, so this is a standard random walk kind of expression. Meanwhile, this whole cloud is expanding on a time scale, dynamical time scale of r over the velocity of the ejection. And basically, when this diffusion time becomes comparable to or shorter than this dynamical time, the photons can run away from the ejecta and escape to be seen. Prior to that, they're kind of stuck inside the cloud, and they're just ejected along. So if we set those two equal to each other, diffusion time roughly equal to the dynamical time, we see the times when they're comparable is when the optical depth of this cloud is about of order c over v. In this case, is about 10. So it's kind of a standard trapping argument, and suggests that we'll start to see the photons not when it doesn't have to become completely transparent. Optical depth doesn't have to be less than 1. It has to be translucent like this. And so we can estimate how long it takes for that to happen. Basically, the optical depth, by definition, is a density times an opacity, kappa times a radius. Rho kappa is just 1 over the mean free path. This kappa we can just take as some number now. If I have time, I'll talk a little bit more about it. And so again, dimensionally, the density is falling off. It's mass over radius, or mass over velocity time cubed. The opacity and the radius is growing as well. It's velocity times time. So the optical depth is basically just m kappa over velocity times time squared. As this expands and dilutes, the optical depth goes down. And we can ask when this is of order c over v, and so photons stream away. And so solving for t here, we get a characteristic time scale of the kilonova, the TP, or the peak time scale of that kilonova emission. Turns out to be n kappa over Vc to the 1/2 or so. Okay, that's the standard result, or kind of the typical time scale of emission from that cloud. And then again, you can plug in numbers here that we had for the mass and the velocity. This kappa, we take a number like 1 or something for that opacity. There's some numerical factor I've dropped. But this is kind of of order a day or so. So prior to a day, photons really can't get out and things just ejected in this cloud. But about a day or later, we start to see light escaping from our mushroom cloud. And that's the light we're going to see as the kilonova that was actually detected, coincidence to the 2017 neutron star merger. Now, I'm saying photons are escaping from those. Where do those photons come from? What's the energy powering this radiation and keeping it hot? There's kind of two generic possibilities there. One is that, well, the stuff was originally hot. I mean, it was formed in this disk I just erased. As hot stuff gets ejected, it has some internal energy. There's nuclear reactions in the R process that also enhance the heating. You might run a jet through it and shock it and heat it up. So there may be some initial thermal energy just there when the stuff got ejected that's then leaking out. The second possibility, which we'll see is the relevant one, is that there's some continuous heating going on in the source over periods of time, largely because this material, this radioactive waste cloud, is going to be radioactive and decaying with half-lives on order days and weeks and so on, providing a continuous power input to the kilonova. Although another possibility is the kilonova may be continuously powered from some central activity. If there's a black hole here that continues to accrete for days or weeks, or not a black hole, a neutron star, a millisecond pulsar, or magnetar, there could also be continued power injected into the system. And that's actually how we can constrain whether there's a pulsar there or not, because we would expect to see that power if that pulsar had survived. So where does the energy come from? How much time I have? Let me consider the two cases. One is you have some initial energy from the explosion. And we can do a very simple estimate of how bright a kind of source that would be on the time scale of a day when things are leaking out. And you just do it like this. The luminosity of this source is kind of the energy we have initially over the time scale it's leaking out that we just solved for here, which is going to be roughly a day or so. But now we have to take into account that the energy was injected in the system when it was a small thing, about 100 kilometers or so. And by the time we reach a day, it's expanded to something like 10 to the 10 kilometers. And in that process, a lot of this internal energy has been lost to PDV work. In fact, this is a radiation pressure-dominated gas, so the adiabatic index is 4/3. And so the energy is falling off like 1 over R as it does for a gamma 4/3 gas. And so the actual energy you have left to radiate at about 2p is the ratio of the initial radius to the final radius, velocity times this time, which is a very small number, something like 10 to the minus 8. So it's very inefficient to try to radiate any initial energy, because all of that goes into basically adiabatic expansion and work. In fact, we can make an estimate here. You could say, well, as I estimate this initial energy as some multiple of the kinetic energy. Some processes like strong shocks would give you some equipartition of kinetic and internal energy. At least the internal energy can't be too much larger than that. And if you do that, you'll get a value something like, you plug in all the numbers that we have here, you'll get a luminosity about 10 to the 38, R naught over 100 kilometers ergs per second. So that's like 10,000 times the luminosity of the sun or so, but it's about 3 orders of magnitude or more dimmer than the kilonova that we actually saw. So there's really no way to power this with its initial energy unless the initial radius that was injected was much larger than 100 kilometers by some very large factor. And there are people who speculate about ways you might get some mass sitting out at solar radius or tens of solar radius or something. And that might be contributing. But it seems a little artificial to have matter starting that far out. Yeah?
Presumably there's electrons that are also being shot out of this thing. Do they free stream out, or are they also stuck in this cloud?
What do you mean?
I mean, you're talking about the free stream length of the photons, I assume, within this cloud, right? But electrons can. I'm not sure what their free stream length is. Are they also stuck? With this cloud,
they'll
or
be
are they just shooting out.
Densities are high enough that those will be tightly coupled to the basically hydrodynamic, so they'll be all coupled into this plasma.
I see.
So they won't be able to. You can basically treat it hydrodynamically at these speeds. So if it's not the initial energy, we need some way to continually heat this ejecta up and power it. And that's where radioactivity comes in. Again, you could also invoke some central engine activity, but radioactivity is the common one. And the idea is you have stuff decaying here that's giving you some radioactive power. You can estimate that as well. The radioactive power of some isotope over time. Well, if we have a total mass m, and we say there's some energy, ergs we get per gram from radioactivity, we can estimate that number, just say, well, maybe we get about an MeV per nucleon that decays. Figure out what that number is. And then for an isotope, we just give the standard exponential decay on some, decay time scale, TR. And so that would be the heating from a single radioactive isotope. But in this kilonova cloud, we actually have lots of different isotopes. You kind of make a big splash across the periodic table. And so it's not just one isotope that's contributing, it's a lot with different half-lives. And so the argument made in the clever 1999 paper by Lee and Paczynski, which is the one that kind of introduced this whole idea of a kilonova with arguments along this line, said, well, let's just assume we have lots of different radioactive isotopes with half-lives that are distributed logarithmically in time, since nature likes to distribute things in the log. Right? A lot of things happen like that. And so then you can just say integrate up all the different isotopes with a logarithmic distribution. And you can do this integral, not hard, and you get, to factors, basically em over t, so you get 1 over t dependence. Right? And we can actually plug in numbers here. When you do the detailed calculation with these big nuclear reaction networks that have 1,000 isotopes or something, you find something very similar. This is something 10 to the minus 41 liters per second times the mass over 10 to the minus 2 solar masses times t to the minus 1.3. So it's slightly steeper than that argument. And actually, this factor 0.3 has been argued. Kazak has a paper on this thing. Basically, with beta decay, these are all beta decays of neutron-rich isotopes. Longer live beta decay isotopes have a less energy release. There's a relationship between the energy release and the half-life, and so that can give you a factor of 0.3. But at the rough level, the simple argument works remarkably well compared to detailed calculations. But if you look at the details, depending on the nuclear physics you put into your calculation and the details of what you think that YE distribution looks like, this can vary up and down by factors of several or so. And this is essentially how we think what's powering the light curve, and it's how you could estimate the mass that got ejected there. Essentially our light curve is going to look like this. So here's the radioactive power, just kind of falling off like a power law. We may steepen at later times, because this is actually just the energy that's released in radioactivity. A lot of that comes out in MeV electrons, and so only a fraction of those electrons may actually deposit their energy and thermalize inside the ejecta. In fact, something Jenny Barnes has worked a lot on. You can put in an extra factor here, something like T over some characteristic thermalization time. You can work out analytically something like this, that at t, this might be a week or so for typical values. After that, the electron stops sort of heating, and the time dependence steepens to something like 2.5. But if this is the radioactive heating, then the light curve looks something like this that we actually see. So, at peak, this is roughly this time scale where tau is C over V and things stream out. Earlier than that, you're still heating stuff, but nothing can get out, so it's just sort of stuck inside. And then at some later time, tau is of order 1, and it's optically thin, and the light curve that you see will basically just track directly the heating that you observe. So you can follow these things to late time. You can say maybe interesting things about what isotopes might be dominating out there. You can measure there's an isotope that dominates the half-life. But essentially, this peak here is going to be set by how much mass is involved, and since this luminosity was something several times 10 to the 41, almost 10 to the 42 at earlier times, you get a mass of about 0.05 solar masses as a rough estimate. And that's what fed back into those constraints on tidal deformability and all that. Now, a lot more goes into this. We've made a very simple model here, spherically symmetric. If the debris has some asymmetry to it, there's going to be some viewing angle dependence. It'll be brighter or dimmer from certain points of view. There's whole details of opacity in terms of what the composition is and how we can entangle that, as well as the things we've said about the nuclear heating rate and so on. So there's a lot of areas to try to further understand and interpret the emission that we see. And that'll be interesting to do in the next few years from a theoretical point of view in the modeling. And hopefully, from the observational point of view, we'll get some nearby neutron star mergers and see the variety of different kilonova we can get. And whether this mass here is fixed around this value or whether it can vary up and down by orders of magnitude and so on. So hopefully, exciting times ahead. Thank you so much for your
So you mentioned that the expanding cloud is a radiation pressure dominated, essentially, cloud. And there could be also asymmetries, as you also mentioned. I'm curious as to how much we can trust the theoretical kilonova models about including their radiation transport, and how that might relate essentially to these estimate for the ejected masses. If there are any uncertainties, how much it can vary, maybe how low that could be, because that number is used by people to place the lower bound, as you mentioned, on the tidal deformability.
Yeah, so it's a good point. How well do we know, extract this from modeling that how bright the kilonova is? And you're right, asymmetries will be some effect, and roughly, if you have an ellipsoid like this, it's an axis ratio. Roughly speaking, we've done transport calculations like this. The brightness as a function of viewing angle is very roughly speaking the kind of projected surface area that you get from any point of view. If you thought of this as some black body emitting surface. So if this is 2 to 1, it might be twice as bright from this angle as it is, from the pole as it is from the equator. And so depending on how aspherical the ejecta is, and the models, the winds at least are not so aspherical, but the tidal debris can be aspherical. You might have effects of an order factor 2 or something due to viewing angle effects that would have to be folded in somehow by trying to extract the. You have to know something about the geometry and the inclination, which we both don't know so well, but we can try to constrain. And then there's a whole technical subject I didn't have time to get into in terms of the transport and the opacities as photons scatter out the way. And there's actually a very strong dependence of the opacity on the composition. So the heavier elements are maybe 100 times more opaque than the lighter elements. And that means that depending upon the opacity, if you have lighter elements, they tend to have a fairly brief light curve here, peaking in about a day. If you have heavier elements, they have a much higher opacity, and so this diffusion time is not. If this is 100 times higher, it might not be days, it might be a week or so. And so the light curve looks something like this. Happens much longer time scale and somewhat less luminous. And actually, the common picture here is that you might have this superposition of a light and heavy emission. So maybe the superposition of these two gives you something like this.
Yeah, what fraction of this event, of the energy in the event, is deposited in neutrinos, and how well do we know that number? Do you know?
Well, once you merge the neutron star, there's a lot of, you have a lot of energy and thermal energy of that neutron star, something similar to a supernovae in 10 to 53 ergs. And that all starts to get radiated away, but likely that neutron star collapses to a black hole before you can radiate away that energy. And neutrinos, like it happens in a typical supernova. So probably a lot of that energy just gets sucked into the black hole and contributes to the mass of the black hole. And that's where most of it goes, the gravitational waves in the black hole. This kilonova kinetic energy you can calculate for this mass and velocity. It's something close to 10 to the 51 erg, so somewhat similar to a supernova explosion energy. But a couple orders of magnitude lower kinetic energy than the total energy, gravitational energy of the system.
So if it was some sort of additional source of cooling that's not taken into account from some sort of new physics, like do you have a feeling for how much you could constrain that source of new cooling? I mean, let's say neutrinos were radiated way more than you'd expected. I mean, how much would we be able to put some constraint on new physics in that sort of way? You have a feeling for that?
You can play you can maybe think about a new dark matter particle or something that has
As an example, yeah.
and maybe it radiates energy away, comparable, even greater than a supernova if you have a relatively strong coupling constant. I think I thought about this. There may be some narrow range of parameter space where it does something interesting, but probably here it doesn't do much that's detectable. I think for supernova, those constraints are more interesting because they're nearby. The neutron star lasts longer, and you can actually put some more stringent constraints on sort of a new particle or something that might be radiated and hence be detectable, say on Earth, or would mess up the supernova. Here, it's not so clear, at least in that specific example, whether there would be much to constrain, but it's something worth definitely thinking about.
Thanks.
Okay, see you all at 5.